In 1944, a group of 36 men volunteered for this totally grueling 6-month starvation diet.
Right, the Minnesota starvation experiment.
Yeah, and their bodies reacted predictably, drastically slowing down to conserve energy. But here's the part that just defies common sense.
It really does.
When they finally started eating normally again, their metabolisms did not speed back up.
Yeah.
Their bodies continued to hoard energy, like acting as if they were still starving.
Which is wild.
It is. And decades later, modern studies of extreme weight loss show the exact same phenomenon. People walking around years later with a metabolic rate essentially trapped in survival mode. Welcome to the deep dive.
Yeah, it's just a perfect illustration of how deeply we misunderstand our own biology.
Totally.
We talk about metabolism as if it's like a biological furnace. We picture shoveling food into a fire, and we think of it as a fixed speed limit that dictates our weight.
Right, you hear people say, oh, I have a fast metabolism or a slow one.
Exactly. Or we're always looking for a pill to stoke the flames.
Which is why today's mission is so critical. We are diving into a stack of anatomical and physiological research to completely rewrite that definition for you. We are going to uncover the actual truth behind how the human body builds up and breaks down molecules to power life.
And to do that, we really have to start by throwing out the furnace metaphor entirely.
We do.
Because when you look at the physiological reality, metabolism isn't a furnace and it certainly isn't a single speed. It is a complete, dynamic, incredibly complex set of chemical reactions occurring inside a living organism.
Okay, let's unpack this, because if we assume you already know the basics of, proteins and carbs, the sources give us a much smarter way to visualize this. Imagine a massive, sprawling city made entirely of Lego blocks.
I love this analogy.
It works so well. So metabolism is split into two simultaneous operations in the city. First, you have catabolism. This is the demolition crew.
Right, the breakers.
Yeah. They are violently smashing apart Lego castles like the nutrients you consume or the tissues you've stored to harvest the individual blocks. But more importantly, breaking those bonds releases stored energy. In the body, that energy is captured as ATP.
Adenosine triphosphate, the universal chemical currency of life.
Right. Then you have the second operation, which is anabolism. This is the conscription crew. They take that freshly minted ATP and those loose Lego blocks to build something entirely new.
Like a spaceship.
Exactly. Or, in biological terms, muscle fibers, DNA, or cellular membranes.
And the crucial shift in perspective here is that these are not alternating shifts. Fitness marketing often tells you that you burn energy during the day and build muscle at night.
Yeah, like it's a day and night shift thing.
Right. But that is fundamentally incorrect. Every single cell in your body is running both anabolism and catabolism constantly, simultaneously, and continuously. They are a coupled, dependent cycle.
Because without anabolism, catabolism is just uncontrolled decay, right? You would literally just dissolve.
You would. And without catabolism, anabolism has no power grid to draw from. You cannot build the new structures without harvesting energy from the old ones. They share the exact same chemical economy.
Which makes the human body sound less like a machine and more like a constant, chaotic construction site.
It really is.
But if that is the modern understanding, how did we actually figure this out? Because looking at the history in these sources, the furnace idea wasn't just a bad metaphor. It was the prevailing scientific dogma.
It was. To understand how we arrived at a mapped network of chemical reactions, you have to look at the 19th century debate over vitalism.
Right, vitalism.
Yeah, so the term metabolism itself, from the Greek metabole, meaning change, was introduced to biology around 1839 by Theodor Schwann. At the time, early chemists were starting to view the animal body like a combustion engine.
Okay.
But the majority of the scientific community pushed back hard. They believed living chemistry was impossible to replicate in the lab because it required a magical vital force.
Wait, so they basically thought life was fueled by magic?
Essentially, yes. A spark of life that operated completely outside the laws of ordinary chemistry.
Which sets the stage for one of the most fascinating experiments in the sources. It's 1897, and this German chemist named Edward Buchner decides to test this vitalism theory using yeast.
A brilliant experiment.
So he takes living yeast cells, mixes them with ordinary sand, and physically grinds them to a pulp. He utterly destroys the cellular structure, presses out the liquid, filters away anything that could possibly be considered alive, and is left with this dead, cell-free juice.
He called it zymase, and what he observed next actually won him the Nobel Prize.
He found that this dead biological smoothie could still ferment sugar into alcohol and carbon dioxide.
Easy.
And fermentation is a catabolic process. But wait, I want to make sure I'm grasping the philosophical weight of this. Buckner completely eliminates the living organism and the chemical reactions just blindly continue on their own. How does that definitively disprove a vital force?
Because it proved that the reaction was driven by a physical substance, what we now know as enzymes, not a mystical state of being alive.
Oh, wow.
Yeah, Buckner showed that metabolism is mechanism, not magic. It is just chemistry. If you have the right enzymes and the right substrate, the reaction will occur, living cell or not.
That shifts the entire paradigm. If it's just chemistry, it means it can be isolated, manipulated, and mathematically measured.
Precisely. That realization allowed scientists like Hans Krebs to later map out specific, predictable metabolic pathways. It turned a philosophical abstraction into a quantifiable network.
Right.
And speaking of quantifying, this mechanistic view led directly to the work of Wilbur Atwater in the 1890s.
He built the human calorimeter at Wesleyan University, right? The room-sized box where they sealed people inside to measure their heat and vapor output.
Yes. The Atwater calorimeter was the first time metabolism was measured directly and rigorously in a living human.
And the math they did in that 19th century box is still haunting us today. They calculated the energy yield of macronutrients, which gave us the 449 calorie labels.
4 kilocalories for a gram of carbs, 4 for protein, 9 for fat.
Yeah, the ones that are printed on the back of literally every food package in the grocery store right now.
It is incredible longevity for a single experiment.
Yeah.
But here is the limitation of the Atwater box. It measured a system perfectly at rest.
Right, just a guy sitting in a sealed room.
Exactly. To understand the true dynamic nature of the anabolic and catabolic cycle, you cannot just look at someone sitting in a box. You have to look at what happens when the machinery is pushed to its absolute physical limits in the real world.
Okay, if the system is as mechanical and predictable as Buckner and Atwater proved, we should be able to see it physically shift gears under stress. Let's look at extreme catabolism first. The sources point to a very specific painful phenomenon, the marathon runner's wall.
Usually hitting right around mile 20.
Yeah.
To understand the wall mechanically, you have to look at the body's fuel storage. You store carbohydrates as glycogen, primarily in the liver and muscles. The average person holds about 400 to 500 grams of it, representing roughly 1,600 to 2,000 kilocalories. Glycogen is your fast-burning fuel. It is rapidly catabolized to produce ATP.
It's the Lego castle that requires the least amount of effort to smash apart.
Yes, exactly. But a marathon requires a massive, sustained output of ATP. And for most runners, right around that 20-mile mark, the glycogen tank is completely exhausted. The fast fuel is just gone.
So the body is suddenly caught in a massive energy deficit. It has to find a new source of ATP immediately, which forces it to switch to catabolizing stored fat.
And that transition is not smooth. Fat yields significantly more energy per gram than glycogen, but it is incredibly slow to process.
Right.
Fat oxidation requires far more oxygen and a much longer, more complex chain of enzymatic steps to finally yield ATP.
Here's where it gets really interesting. Hitting the wall is often described as a mental breakdown, but it is actually a deeply physical, biochemical event. It reminds me of driving an older hybrid car.
Oh, that's a good comparison.
Yeah, you are cruising silently on electric power, and when that battery suddenly dies, the car violently lurches. It abruptly stalls out for a split second while the heavy mechanical gas engine is forced to turn over and kick in. You literally feel that mechanical shift in your bones.
That analogy holds up perfectly. The crushing fatigue a runner feels at mile 20 is the felt experience of their metabolic pathways being dictated by this sudden unavailability of raw materials. The fast machinery shuts down, the slow machinery fires up, and you feel the lag.
So that's extreme catabolism, the breakdown side. But the sources also highlight extreme anabolism forcing the building phase to its limits. And one of the clearest examples comes from the 1988 Seoul Olympics.
Ah, the infamous 100-meter dash in Ben Johnson.
Yeah, he ran a world record 9.79 seconds, won the gold, and days later tested positive for stanozol, an anabolic steroid. He was stripped of the medal. But purely from a physiological standpoint, what is that drug actually doing to the machinery?
Synthetic anabolic androgenic steroids are a masterclass in exploiting the building side of metabolism. They chemically mimic testosterone and bind directly to androgen receptors inside the muscle cells.
Okay.
When they bind, they essentially act as transcription factors, signaling the cell's DNA to massively accelerate protein synthesis.
So they are essentially flooding the Lego city with millions of extra construction workers, forcing them to build new muscle tissue far beyond the body's natural limits.
And significantly accelerating recovery time. It is a direct exogenous override of the anabolic pathway.
Okay, this brings us to the most frustrating contradiction in all of this. If the body's fuel system is so mechanical that we can predictably stall it out at mile 20 in a marathon, or override it to build massive muscle using a steroid, you would assume the average person could just engineer a simple calorie deficit to lose weight predictably.
You would think so.
But that brings us back to the starvation study we opened with. The body fiercely fights back.
This is the great calorie illusion. The diet industry relies on the calories in, calories out model, which assumes your resting metabolic rate is a static number. But your metabolism is not a passive engine. It is a highly reactive, evolutionary survival machine.
Let's dig into the mechanisms of that survival machine. We mentioned Ansel Keys earlier. In his 1944 Minnesota starvation experiment, the men on the semi-starvation diet saw their basal metabolic rate, the energy burned just to keep their organs functioning, drop by 40%.
Right. And the critical detail is that the drop in metabolic rate was disproportionately larger than the amount of body mass they lost. Their machinery didn't just shrink, it actively became stingier with energy.
And as we touched on at the beginning, that stinginess lingers. The researcher Kevin Hall proved this by studying former contestants from the television show The Biggest Loser.
Yes, a very famous study.
These were individuals who endured extreme, rapid weight loss through massive calorie restriction and intense exercise.
And Hall found that 6 years after the competition, most had regained the weight, yet their resting metabolic rates remained suppressed by hundreds of kilocalories a day compared to what would be normal for their body size.
Wow.
The metabolic thermostat does not easily reset because the body still perceives a threat of famine.
Okay, so calorie restriction triggers a survival shutdown. But what about the other side of the equation, burning more energy through movement? We are always told that if you just exercise more, you will burn off the extra food.
Which brings us to the groundbreaking research of evolutionary anthropologist Herman Pontzer. He spent years studying the Hadza people in Tanzania. They are a highly active hunter-gatherer society. They walk, climb, and forage for miles every single day.
So logically, their daily energy expenditure should be just off the charts compared to a sedentary office worker in a Western country.
That was the assumption. But when Pontzer actually measured their total daily energy expenditure, he found it was virtually identical to sedentary Westerners of a similar size.
I have to pause here because this completely breaks the math we are taught. If a Hadza hunter burns 800 calories walking 10 miles, and I burn 0 sitting at my desk, how can our total daily burn be the same? Where did those 800 calories go?
To understand this, you have to grasp the concept of metabolic flux and the constrained energy model. Your body's operating on a strict energy budget. If you dramatically increase the energy spent on physical activity, your metabolism will quietly balance the books by defunding other unseen physiological processes.
Wait, what kind of processes is it secretly shutting down?
Things you wouldn't consciously notice. It will dial back background systemic inflammation. It will reduce the production of stress hormones like cortisol. It may even suppress reproductive hormone levels.
Really?
Yeah. The machinery redirects energy away from the immune system and cellular upkeep just to afford the calories you spent running.
So a 5-mile run doesn't give you a free 500-calorie pass. Your body is just borrowing that energy from your immune system to keep your total daily expenditure tightly constrained. That completely shatters the myth that a slow metabolism is the primary driver of weight gain.
Genuine, significant variations in resting metabolic rate between healthy individuals of the same size do exist, but they are incredibly rare. The constrained model shows us that human energy expenditure is remarkably uniform across vastly different lifestyles.
Which also means all those popular metabolic hacks are largely nonsense. Eating spicy food or taking ice baths to boost your metabolism.
The thermogenic effect of capsaicin in spicy peppers or shivering in a cold shower is biochemically real, but the actual impact is just a rounding error. It might elevate your energy expenditure by a fraction of a percent for a very brief window. It will never outpace a hypercaloric modern diet.
And while we are busting myths, we have to address the claim that building muscle will turn you into a fat-burning furnace, because muscle burns 50 times more calories than fat at rest.
A massive exaggeration.
Yeah.
Oh yeah. Muscle is definitely more metabolically active, A kilogram of resting muscle burns roughly 13 kilocalories per day, while a kilogram of fat burns about 4.5 kilocalories.
Okay, so it's a difference.
It is a meaningful difference, nearly 3 times as much, but nowhere close to 50 times. Building muscle is excellent for metabolic health, but it does not give you a roaring furnace that burns off a bad diet while you sleep.
If the metabolism is this tightly regulated, fierce survival mechanism, it makes sense that manipulating it for aesthetics is difficult. But we need to pivot, because the sources make it clear that this interconnected network of building and breaking isn't just about weight loss.
Not at all.
This biology dictates the absolute extremes of human survival. When you look at modern medicine, metabolism is the primary battlefield.
Walk into any intensive care unit, and you will see this machinery operating under the most extreme conditions possible.
The sources specifically mention that critically ill patients enter a state of severe catabolism. Why does trauma force the body to eat itself?
When a patient is fighting sepsis or recovering from a massive physical trauma, the energy demands of the immune system and the vital organs just skyrocket. If the patient is incapacitated and cannot consume calories, the body faces a crisis. To survive the next hour, it initiates a hypercatabolic state, violently breaking down its own skeletal muscle protein to harvest amino acids for energy and tissue repair.
So a patient lying perfectly still in an ICU bed is undergoing an invisible, violent demolition. Their body is essentially choosing controlled decay to fund the survival of the brain and heart.
Exactly. This is why clinical nutrition in an ICU setting is so critical and aggressive. Medical teams use specialized feeding protocols explicitly designed to blunt that rampant catabolism. They're trying to force the metabolic machinery back into an anabolic state so the patient can actually heal rather than waste away.
It highlights how delicate that balance is, and this incredibly complex chemical network is also the foundation of pharmacology. Every drug we swallow has to navigate the system, specifically the liver.
The liver is the body's primary chemical refinery, and it utilizes a family of enzymes known as cytochrome P450. These enzymes are responsible for metabolizing almost every foreign compound you ingest, from ibuprofen to chemotherapy drugs.
But how do they actually process a drug? Do they break it down for energy?
No, in this case, the metabolism is about detoxification and excretion. Most drugs are fat-soluble, which means they would easily pass through cell membranes and accumulate in your fat tissue forever.
Oh, that's not good.
Right. So the P450 enzymes chemically modify the drug, often by attaching an oxygen molecule to it to make it water-soluble. Once it is water-soluble, your kidneys can filter it out, and you excrete it in your urine.
But the sources note that this process varies wildly between people.
Because of genetic variations in the P450 enzymes. One person's enzymes might be so aggressive that they chemically tag and excrete a drug before it even has a chance to work. Another person might have a sluggish variant, meaning a standard dose of a medication builds up to toxic levels in their blood. Understanding metabolism is the entire key to personalized medicine.
And speaking of toxic buildup, we have to talk about cancer. The sources bring up Otto Warburg, a scientist who made a bizarre discovery about how tumors fuel themselves.
In the 1920s, Warburg noticed a strange metabolic quirk in cancer cells. Normal, healthy cells use oxygen in a highly efficient process to extract maximum ATP from glucose.
Right, respiration.
But Warburg discovered that cancer cells actively shun this efficient pathway. Instead, they preferentially ferment glucose, even when they are swimming in plenty of oxygen.
Which seems entirely counterintuitive. Fermentation is a primitive, deeply inefficient catabolic pathway, right? It produces a fraction of the energy. Why would a rapidly growing tumor choose an inefficient fuel source?
Because a tumor's primary goal isn't just generating ATP. It is rapid, uncontrolled replication. Efficient respiration burns glucose completely to ash carbon dioxide and water. But fermentation is messy. It leaves behind intermediate molecules, essentially loose carbon backbones.
Okay.
Those leftover pieces are the exact physical building blocks, the raw biomass, that the cancer cell needs to rapidly synthesize new DNA, proteins, and lipids to build the new tumor cell.
So the tumor intentionally runs an inefficient energy pathway because the waste products are the anabolic raw materials it needs to multiply. That is incredibly sinister.
It is. The Warburg effect means cancer cells must consume absolutely massive, disproportionate amounts of glucose to survive. And modern medicine exploits that exact metabolic vulnerability.
By using PET scans.
Precisely. Oncologists inject a patient with a radioactive glucose analog. Because the tumor cells are aggressively hoarding glucose to fuel their inefficient fermentation, they absorb the radioactive tracer rapidly, causing the tumors to literally light up on the scan. We map the cancer by hunting its broken metabolism.
Which brings us to the final frontier in these sources, aging. For decades, researchers have been studying whether manipulating these metabolic pathways can actually delay death.
The most robust finding in the biology of aging is that severe caloric restriction without malnutrition extends lifespan across numerous species, from yeast to mice to primates. By restricting calories, you intentionally slow the metabolic flux. You reduce the massive volume of chemical reactions, which in turn reduces the oxidative stress and cellular damage that accumulate over time. The holy grail of modern aging research is finding pharmacological compounds that can mimic this slowed metabolic state in humans without requiring us to actually starve ourselves.
The more you look at it, the more you realize that the building and breaking of molecules touches every single aspect of our existence. We have covered an immense amount of ground today, transitioning from a historical theory of magic to the absolute cutting edge of survival. Let's synthesize the actual takeaways from these sources so you can carry them with you.
Sounds good.
First, metabolism is not a furnace or a fixed number. It is the continuous, simultaneous, and coupled process of breaking down molecules' catabolism and building them up anabolism.
Second, the chemical bridge between demolition and construction is ATP. Catabolism releases it, and anabolism requires it to build new structures.
Third, Edward Buchner's famous yeast experiment proved that the system is governed by ordinary chemistry and enzymes, permanently ending the belief that living creatures required a magical vital force.
Fourth, human energy expenditure is remarkably constrained. As Hermann Pontzer's research on the Hadza demonstrated, extreme physical activity forces the body to quietly defund other biological processes to balance the budget. A naturally slow metabolic rate is rarely the culprit behind weight gain.
And finally, number 5. Your body is fiercely adapted to survive starvation. Drastic calorie restriction triggers a survival mechanism that suppresses your basal metabolic rate, and as modern studies show, that suppression can linger for years.
The machinery is brilliant, and it is always trying to protect you.
So the next time someone complains about their metabolism being a broken thermostat or tries to sell you a supplement to stoke your biological fire, you now understand the reality. You know about the profound, ancient, and highly regulated network of chemical reactions that is actively building and breaking inside you at this exact second.
And looking at the full scope of this research leaves us with one incredibly provocative question to consider. We have established that the human metabolism is an ancient survival machine. It evolved over millions of years specifically to constrain energy, to adapt to famine, and to keep us alive through brutal periods of starvation.
It is perfectly tuned for a world of scarcity.
It is. Which means we have to ask, are our modern global epidemics of metabolic syndrome, obesity, and type 2 diabetes really the result of our bodies being broken? Or is it possible that this incredibly sophisticated, ancient machinery is working exactly as it was perfectly designed to, but it is just drowning in a modern environment of endless calories, processed foods, and unprecedented comfort?
We aren't failing. Our biology is just surviving too well. It turns out that biological furnace everyone talks about isn't a furnace at all. It's a masterpiece.